In this episode, we're going to talk about stack frames. If you don't know what a stack is yet, go back and watch our video on stacks because it's very important you understand what a stack is and what the push and pop operations do on a stack. If you don't know what that is, go back and watch that, learn that, and come on back when you're ready. But let's continue. So let's move into the project directory for today's lesson, which is Intro to Reversing / Exercise 2 Stack Frame. So let's cd into that directory and do an ls, and we see we have a couple files here. So let's go ahead and look at stackframe.c. And this is a simple C example program that helps us illustrate the stack frame. We have a function here, main, take argument count and the actual argument vector, and all it does is it stores some space for the radius and then calls this function printf, which is going to display this string to us. Please enter the radius of the circle. And then it's going to read in our response and store the value in the variable radius. Then it's going to call circle area, and this is what we're interested. We're interested in what happens when we call circle area passing the value radius. Let's look at the function for circle area. We have a variable int pi equals 3. Yes, we know pi is really 3.4, 3.14, something, which is not an integer, but just for the sake of ease and understanding, we're going to just say it's 3. Then our function takes pi, which is 3, multiplies it by the value that we passed in, radius, and then simply prints out the results. The area of the circle rounded down is, and then the value of area. So let's look how this translates to assembly code. So what I'm going to do here is I'm going to just put the data side by side. So I'm going to also move into that directory. And now let's do an obj dump on that file stack frame. So remember from last time, obj dump -j.text -d for disassemble. That's a capital D. It's important. In Unix, lowercase and capitals are completely different things. The name of the file, which is stack frame, that's the name of the binary we want to assemble. And I'm going to go ahead and add that -m Intel option because I like to see things in Intel format. If you prefer AT&T format, more power to you. In my lessons, I'm going to explain things in Intel format because I get very confused by AT&T format. And then let's move up to the function circle area. Let's find that. Where is that? There it is. And what we have here is the function circle area. Right here. Okay? So let's analyze this. Now, I'm going to explain the stack frame and calling the variables or calling the function in the calling convention that Linux uses on 32-bit Intel platforms. Each operating system calling convention or architecture, as well as the compiler, depending, can be actually different the way it does things. But this is a very good example of how traditional stack-based calling conventions work, and it will help us to understand what we're talking about. So let's understand how 32-bit Intel on Linux handles the calling of a function. So to understand that, we actually are going to go down to main. Okay. And what we need to understand is how the function call happens. And what happens is we are going to push our arguments to the function to the stack right before we issue the call instruction. And don't worry about figuring out all this means yet. Just trust me that EAX holds the value radius at this point in the function main. At this point on virtual memory address 804.856D, EAX currently holds the value that the user would have inputted for the radius of the circle. And the way it works is when you call a function, you are going to push onto the stack the variables from the far right variable to the left. So we only have one variable here, so we push EAX, which is radius. If we had another variable here, for whatever reason, let's just call it, I don't know, diameter. That would be pushed first before radius is pushed. So you would see that push happening probably in this line, which is sub ESP minus C in hex, but we only have one variable, okay, or one parameter to the function. So we push it onto the function, and then we call the circle area function. Now, what happens when we call the circle area of the function is the processor is actually going to find the next address of the next instruction. In this case, this one right here, 804.8573, and it's actually going to also push that to the stack. Because we actually need to know when we return from the function where to go back and continue executing code. So it's going to push that to the stack. And then what's going to happen is the processor, since the call function happens, it's going to jump basically to this address. Maybe jump is the wrong word to use, but it's going to redirect its flow of execution to the circle area function. So let's go and find that. And here it is. Now let's go ahead and actually load this into the online disassembler. So I'm going to go ahead and close this window. And I'm going to bring up my online disassembler window. And I'm going to go ahead and click Start Disassembling. And I'm going to choose File, Upload File. Choose the name of the file, which is in the directory exercise 2 stack frame. And again, we want the binary file, not the C file stack frame. Choose OK. And it's going to go ahead and load this up. But before it does, it's going to ask us for options. And I'm going to go ahead and set the Intel syntax option. So it doesn't choose AT&T, which I believe it chooses by default. Go ahead and click OK. And here we have the disassembly. Now we can see here on the left we have symbols. Let's go ahead and click right to main. And main shows up. Okay. And again, we can view this in graph mode. But we'll go ahead and just click on the disassembly. And before we get into that, I want to show you one of the features we talked about in the first video, strings. I mentioned that the online disassembler will find strings that exist in your program, which are usually not code, but things that are useful for the programmer and the user. For example, the text, when we say, please enter the radius of the circle, shows up here, and the address that that text, that string, is stored at. In this case, it's 804.8650. Just the same, when we print out the output, the area of the circle, rounded down, is whatever it is. That shows up at address 804.8620. And this is very, very useful. As you do more in-depth reverse engineering, I find that using strings, especially error messages, really reveal a lot of what the code is doing and helps you fill in very quickly various structures and variables. And let's look at the code for circle area. And I can go ahead and click on circle area, which is very nice. You can see it says call circle area, and I can click on that and it will jump immediately to circle area. So now let's look at the actual code for the function circle area. And whenever you enter a function, you are going to start with what's called the prologue. And the prologue is to the function is code that the compiler puts in that's not necessarily the code the programmer wrote. In fact, it's not the code the programmer wrote, but it sets up the function and sets up various memory addresses to store variables, save variables that the compiler saves registers, I should say, that the compiler needs to save, and so forth and so on. So in this case, push EBP is the first statement of the prologue. And what this does is this backs up the old register EBP because we're about to destroy what was ever in EBP. So one of the neat things that you can do here in the online disassembler is you can put a comment. I'm going to left click on the line, or I'm going to click on the line, left click comment, and then just put back up old value of EBP. And so now you can actually see, as you make sense of things, you can see what your thoughts were previously on what things do. So EBP is important because often EBP on Intel 32 systems is used as what's called a frame pointer. And remember, we're talking about the stack frame, and the frame pointer basically just points to the beginning of the part of the stack that is corresponding to this specific function's stack frame. So, what is the stack frame? Well, the stack frame pointer is actually what the value of the stack frame was when we entered the function. So, we're going to destroy EBP, so we're going to back it up first, because later on we will actually restore it. And that's what this function, this opcode, leave does. And I'm going to comment that, is leave simply just restores the old stack frame pointer. Since we have no registers we need to back up, we will move to the next step, which is to allocate space for our local variables. Now, local variables are the variables that are local or defined within the function. In this case, int pi is a local variable for circle area, and int area is a local variable. So we need to make some space on the stack for those variables, because those variables only exist during the running of this function. So we will store them on the stack. So the compiler subtracts from ESP the value 18, which is hex code for 24. So it's going to store 24 bytes for local variables. Now, it may not use all those bytes to actually store things. The compiler will often pad space allocations to certain boundaries because the CPUs perform better as data is what's called aligned. So that's the stack frame usually contains the parameters of the function pushed on the stack from right to left, the return address of the code that we will jump back to once we have completed the function, any space for backed up registers, and space for local variables. So we've now subtracted ESP. So let's go ahead and comment that for allocate local storage. This time I'm just going to use a shortcut for setting a comment, which is semicolon. Set frame pointer. Good. And now what we see here in this line, we move the value of 3 into EBP minus 10, or in this case, it's actually minus 16, because 10 hex is 16 in decimal. So what this is doing is this is actually setting the value of pi, right? Because pi is 3. When dealing with local variables, they are usually at an offset less than EBP. So they would be EBP minus some number, and values set into the function as function parameters are usually a positive offset from EBP. Like you can see down here, EBP plus 8 is actually the value of the radius. So let's go ahead and just comment that. Move 3 into the space set aside for the variable pi. Now in the next line here, we are going to actually do the moving of pi into EAX, because we're going to use EAX when we use this instruction. So let's just go ahead and comment this. And this isn't really the purpose. We want to learn about stack frames, but I'm going to go ahead and walk through all the code in this function since it's small, and it sometimes helps to learn the whole thing by just going through all the code. But at this point, after sub ESP is done, this is the end of the prologue. So the prologue begins at push EBP and ends, the last part of the prologue is sub ESP. Okay? So now we are actually into code here. This move D word pointer EBP minus 10, 3 is the first code that corresponds to the instructions that the programmer wrote, in this case, int pi equals 3. So here we're just setting up the actual multiplication of pi times radius. Here we're actually doing the multiply. IMul, which is multiply, EAX, which we know holds, and we can actually go ahead and type that in there. EAX is pi on this line. And now we multiply EAX by D word pointer, EBP plus 8. And remember I mentioned EBP plus 8, or any offset from EBP that's positive, is a parameter that was passed to the function. Why is it plus 8? Because EBP was set to the value of the stack pointer immediately after we pushed the old value of EBP. So to get back to the actual data that was pushed on the stack, we have to actually go up 8 bytes. We have to go past the backup copy of EBP, which is 4 bytes on 32-bit Intel, and we have to go back past the return address that we pushed when we entered into the function, and then we actually get back to where we pushed the value of the function, of radius. And if we go down here, remember we did push EAX, that was a value of radius, then we called circle, which caused another push of the next address, and then up here we pushed EBP. So to get the value of radius, it's 8 away from where the stack pointer is pointing to. Okay? So this is just simply radius not radius, area equals pi times radius. And that's computing the value of area. So let's actually not say area yet, because it's not stored back at area. At this step in the assembly, having trouble here. Let's try that again. It's actually EAX is currently holding the value of pi plus radius. And in this instruction, we move EAX back to the space we allocated to hold the value of area. So here we have area equals pi times radius, or whatever EAX held. Okay. Now, the next instruction is just a compiler specific, I guess you would call it an optimization. It's subtracting 8 from the stack because it's setting up, aligning the stack the way it wants to be for the next function call. So this doesn't actually correspond to any code that the programmer wrote. It's just a compiler optimization. So we're not going to talk about that. And then we move, so we know here that EBP minus C is actually the variable storage location of the variable area. Here we're now actually pushing this onto the stack for the next function because we're going to print out the value of area. So we're going to push this. This is actually parameter 1 of the call. I'm sorry, it's going to be parameter 2 of the call to printf. And then we push in parameter 1 of the call to printf, which was the string that we wanted to print. Remember that? Please, the area of the circle rounded down is whatever. And remember we mentioned that was at address, when we looked at the strings, it was at address 804.8620. So we see here, this address is the address we push. So this is the address of the string to print. And remember we mentioned that the printf statement was the area of the circle is, and then area. So remember we push from the right left. So the first thing we pushed was actually area, and then we pushed the string. Then we call, and I didn't want to do that, we call printf. So let's jump back to where we were. We were in circle area. Okay, good. So we call function 804.8390, which if we look at that, this is going to be the call to printf, but it's kind of hidden. Don't worry about that too much right now. This is actually printf. So knowing that this is printf, let's go ahead and say call printf. So it's easier for us to read in the future. Then we're going to add, we're actually going to clean up the stack because after the function call returns, before it we subtracted 8 from the stack and then pushed 2 more values to the stack, which actually increased the stack by 16 bytes total, or hex 10. So this is just clean up the stack, or not clean up. I guess call it adjust the stack. The no-op, I honestly don't know why it's got a no-op here. It's probably some type of compiler optimization, maybe dealing with pipelining or something. I don't know. And then we leave. Now, normally, this is here, the leave is part of our function epilogue, which is what happens at the end of the function that's not related to the actual code the programmer wrote, but that the compiler put in there to clean up. Before leaving, we actually would, if we had stored anything, any other variables or registers, we would actually go ahead and pop them off the stack. So we would restore them to the state that they were when they came into the function. And then we leave. And then we do a return. And what leave does is just switches back the value of EBP. Okay, so it basically pops EBP. We can actually, we could say that. We could call it, rather than ret, we just call it pop or restore. And then we call the return opcode. We don't call it, we run the return opcode, which simply pops off the next value of the stack, which is the return address that we had stored, which is to the next line in main after the function, which would be this one right here at 804.8550, and then sets the program counter to that value so that when we're done with the function, we're going to go ahead and return right back. Oops, I'm sorry, that was not the right place. The value it was going to pop off was 804.85 7.3, which is the value of the next instruction after call circle area. So remember, we have a function prologue, we have a function code, and a function epilogue. So remember, the stack frame contains the return address to the next line of code to be executed when we return from the function, the backup of the frame pointer, if you're using a frame pointer. Not all compilers will use a frame pointer. It will contain any backed up registers, and then any local variable space allocations for that stack frame. All right, that's it for today. Thanks for watching, and please come back for our next episode. If your organization requires serious security training, we provide in-house and off-site classes. Check out our website, www.paladingrp.com.